Hi, I'm John Duggan. This is the TheoryStation. This program is the Principles of Math program. The series is called Basic Ideas, and this is installment number 7 in the series. Last time I was talking a bit about functions, and I'm not being very original. I'm going to call this installment more on functions. So we talked about the derivative of a function last time. We were working with a special case, this quadratic function, where you just plug in a real number and it gives you back that number times itself. You can imagine any kind of function with a smooth graph. You can conceptually ask the same question. So in general, suppose your function, again, it has to have a unique value for each x, but suppose it's like this. That's not a quadratic function, but it looks pretty smooth. And if we take a point on the graph of that function, we can put a tangent line up against it, and then we can think, okay, that tangent line has some slope. What is that? Well, in general, that is the derivative of the function. So this slope is the slope of that tangent line is f prime of x. We computed f prime of x for the special case of a quadratic function. It was 2 times x. Well, of course, there's a lot more functions, and we don't know exactly what form the derivative takes, but it is well defined as long as the function has a nice smooth graph. Now, I want to just continue down this path thinking about derivatives, but now in a slightly different context where we have a function and we want to, let's say we want to maximize the function. So what does that mean? It means find the point where the function attains its highest value. So in this picture that I just drew, it looks like, well, one candidate for a maximum would be right at this point here that I've indicated on the x-axis, because the value of the function looks like it's higher than it is anywhere else. So at this particular x, the function achieves its maximum. Well, I didn't draw the rest of the function. But let's just say that's the maximizer of this function. So this is the picture for a general function. For a quadratic function, well, that does not have a maximizer, because if we choose larger and larger x's, the value of the function just goes up and up and up. Okay, so not all functions will have maximizers. If we did a little variation on that, minus x squared, well, now the graph of that would just be flipped upside down, and it does have a maximizer when x is equal to 0. All right. So how is this related to calculus and derivatives? Well, if you just look at these pictures where we have a maximum, so that is here or here, you can see that the tangent line, if I were to draw that in, it's flat, right? So I'll just highlight those tangent lines. And that's pretty intuitive. If a function achieves a maximum, but the slope is increasing, well, then you could just find a higher value of the function by moving to the right. or if the slope was negative, you could find a higher value of the function by moving to a smaller x. So this is a very general result in calculus that anywhere a function is maximized, the slope of that tangent line has to be flat. In other words, the derivative has to be equal to 0. So that's a little result. I'm not going to state it in a very formal way, but the result is that if a function achieves its maximum at x, then the derivative of the function at x has to be equal to 0. All right, kind of a cool result. Let's look at a special example of this and just see why it's useful. And then maybe if you don't know or remember calculus, you want to go learn some more because it's pretty cool. So let's look at an example where the function we want to maximize is, say, x minus x squared. So yeah, how do we do that? Well, we could just guess, I guess, but x can take an infinite number of values, and there's no way we can plug every value of x in there and find this maximum. So we have to be a little more clever than that. Now, the way we express a maximization problem is we say max, and then we write the function that we want to maximize. Now, okay, that's a hard problem. We can't do it by brute force. But we just noticed that, well, if there is a maximizer of that function, we know the derivative has to equal 0 there, right? So what we can do is say, well, suppose x maximizes this function, and let's call this function, we'll just use f because that's just standard. Suppose x maximizes this function, then we know the derivative of the function has to equal 0 at x. So what's the derivative of this function? Well, it's a little bit, I mean, there's two terms here, but the idea is super straightforward. I'll just tell you that the derivative of the function is 1 minus 2x. Okay. So if there is a maximizer, we know that it has to, well, the derivative has to be 0 at that x. We know the formula for the derivative, so that means that 1 minus 2x, right, that's f prime of x, equals 0. So that's easy to solve. X equals 1/2. So if there is a maximizer, it has to be x equals 1/2. Well, now we're onto something because we have a candidate for a maximizer, and it turns out, yeah, that's going to be a maximizer, and we can be more formal about it. But basically, if you just graph this function, the shape of the function is something like this, okay? And so we know that at that point where the derivative is 0, the function's not going to take a higher value anywhere else. Okay, so that means this is a maximizer. We just solved for that. That's x equals 1/2. So what we did was we had this maximization problem that we didn't really know how to solve, but we used that result to convert that to just a simple equation that was easy to solve. So this is an example of optimization. Optimization means you're trying to maximize a function or minimize a function. And you can just see how calculus is incredibly useful in optimization. And this is like one of the simplest examples we could do, but it's much more general. Okay. So let's, I guess I can elaborate on that just a little bit and think about kind of a social sciencey problem where we're going to maximize we're going to choose the scale of a project to maximize the net benefit of that project. Okay, so this is an applied kind of problem. So in a cost-benefit problem, we're going to choose a scale of the project. We'll use X to denote that, and let's suppose that has to be non-negative. And there's going to be some benefit at any scale level. And you can imagine this is measured in dollars if you want, but just some units. And so that's the benefit of X, and there's going to be some cost of X as well. We just need the benefit and cost to be measured in the same units. Okay, so let's just draw some pictures of what these could look like. I'll put the scale of the project on the horizontal axis here. The benefit function might look something like this. It doesn't have to be curved, but I mean, it could be a straight line. But this tells us that as we increase the scale of the project, the benefits increase. So you could imagine maybe this is a public works project where we're building roads and we're measuring the scale of the project is in the number of, the miles of roads that we put in. So, or it could just be the amount of money we're putting into the project. But I suppose you could have too many roads, right? So you could actually imagine if there were roads everywhere, this benefit starts to become negative, but let's go with this. The curvature of this thing means that initially, because the roads are in really bad shape, even small scale projects will lead to a lot of benefit. You can suppose we're filling in potholes. If you fill in the deepest potholes first, that believe me, driving in Rochester, that generates a lot of benefit. And then as you start, getting to the potholes that are not as deep, it's still good to fill them, but the benefits aren't as big. And then after a while, you're filling in cracks, still positive benefit, but again, the benefits decreasing. The increase of the benefit is getting smaller for higher levels of scale. So this curvature of this benefit function is kind of capturing this diminishing marginal returns to scale. Okay. What about the cost function? Well, a typical example would look sort of like this. So here, as the scale of the project increases, the cost increases, which is natural. And the curvature is kind of getting at, initially it's pretty easy to go out there and pay people to put asphalt in the biggest holes. But then as you as you increase the scale, you have to hire more workers, and you might have to pay them more. You might have to pay overtime. It might be harder to find asphalt, and the price is going up. Or it doesn't have to have this curvature. It could be a straight line, but this is getting at this idea of increasing marginal cost. Okay. All right, so we want to maximize the net benefit. So that's benefit net of costs. So from this result that we just did, we know that if there is some scale that maximizes this benefit net of cost, we know the derivative of benefit minus cost is equal to 0. All right. So that there's a little bit involved here, but that boils down to this expression here. On the left-hand side, we have the derivative of this net benefit function. And if x is the optimal scale, that derivative has to equal 0. Okay. Over here in our picture, if you pick an x like this one, you can just see that the net benefit is this difference between the benefit and cost function. And this x that I picked here is not optimal because, well, there's an x here where the difference is bigger, okay? And that looks like it might actually be the optimal one. We can put a little star there if you like stars for optimal things. And anyway, so that would be the optimal scale in this picture. And you can see that, well, in this function, I'm drawing the benefit and the cost, but of course we're maximizing the difference. So it's hard to see the derivative of the net benefit function, but notice, maybe you can tell, if I draw the tangent lines for the benefit and cost functions at that optimal scale, those are the same. Okay. In other words, at the optimal scale, well, the derivative of the benefit function is equal to the derivative of the cost function. Going back to our application here in the maximization problem, notice that this expression here, if we just manipulate it, is the same. So you can just see well, this is just an application of that observation about calculus in the context of an optimization problem, and you can see it in the picture as well. In words, we call this the derivative of the benefit function at x. That's the marginal benefit of increasing scale at x. And the derivative of the cost function is the marginal cost. So at the optimal scale, marginal benefit equals marginal cost. Okay. Intuitively, marginal benefit means it's the rate at which the benefit increases as you increase the scale. Marginal cost is the rate at which the cost increases. Those two have to be exactly equal. And there you go. It would be simple to just apply this to our kind of our example from before, if we let benefit just be linear and cost be quadratic, so the picture would be like so. For this special case, we want to maximize x minus x squared. Well, we already saw the derivative of this is, the derivative is just 1 minus 2x. That equals 0. So the optimal scale is 1/2. Okay, that's just applying the arithmetic from earlier. Anyway, so hopefully this shows you how calculus, it's not just interesting conceptually, it actually has really important benefits when it comes to analyzing optimization problems. And those come up a lot in applications. Like, a simple one is just a cost-benefit problem, but these are very, very much ubiquitous in modeling, in economics and political science. And anyway, so it's a basic tool and one worth thinking about. So that's the end of this installment. I'll see you for the next one.